Good afternoon, everyone. I first like to thank the organizers. It's a very great pleasure for me to be here this week at this symposium. I really enjoyed the lecture and the poster session, and I think ELSI is a very nice place to share ideas and to make them coming true. It reminds me my time when I was a postdoc at the Max Planck Institute. The philosophy was a little bit the same, and it's a great pleasure to get back to the past. I would like also to thank Kosuke. I think we met first time 6 years ago at the end of the afternoon in Moscow. And then 3 weeks later, we wrote a project, very short. We had a chance to get some funding, and he came to Paris. We made a 3-day lab work. We could make a paper, and now it's a pleasure to be here and to see you again. I'm also happy to be a speaker at the last session, because as you can see from this slide, I'm a little bit far from the main topic of the conference and far from all the questions about origin of life. And I would have been very afraid if I would have been in the starting of the conference that after a few minutes you just go away the room and think it's made. I did not went in the good room. So I am more material-oriented scientist, and today I would like to focus on 2 aspects, which are miniaturization and flow chemistry. And with these 2 ideas, I would like to show you how polymer materials can be useful for analytical process, analytical chemistry, and also catalysis, and to combine a catalytic process with an online in situ monitoring of the reaction, taking very, very simple examples. So I will start with miniaturization, and also I will say 1 word about extreme. So going back to the end of the 90s, I was a PhD student, and I was performing my PhD during 2 universities. The University of Lille, I don't know if you heard about the city. Lille is a nice city. It's close to Belgium, but you know, it's very gray, rainy, and foggy. And then when I was making 2 months lab work, I was going to Montpellier. Montpellier is close to Mediterranean, and then it was light, blue sky, windy, but you could have beach volley on February. And for me, it was already a kind of extreme condition of working. But about this PhD, what I remember, I mean, it was one of my first steps toward miniaturization. I was working on the synthesis of chiral polymers meant for life science application and mainly bioanalysis. So the goal was to develop some new stationary phases for HPLC. So starting with porous silica beds, the idea was to deposit these polymers, chiral polymers, on the surface of the porous beds. And these hybrid beds were used to fill in the chromatographic column, and we could have some chiral separation of flavonoids compounds. Then during the PhD came the idea to develop capillary electrochromatography. So in this case, what we did, we were using directly the chiral polymers as a selector, and the polymer could be simply adsorbed on the inner wall of the capillary. In this case, okay, also we could get some resolution. This means separation of enantiomers like derivatives of amino acid. In this case, I think it's a DNP alanine. So if you consider these 2 systems, you may know that a typical dimension for HPLC column is 4.6 millimeters, and for capillary system you go down to 10th of microns. So you have a quite huge ratio between the 2 diameters, and funny enough, it's nearly the same ratio as between the diameter of the Sun and Earth. So it's a kind of miniaturization. Okay, is miniaturization complexity? As you may know, there is no problem to fill a chromatographic column with stationary phases. This is very routine methods. You take a slurry of the bed of your packing material, you just fill in the column using solvent of different density, and you end up with a very well-filled column for 10 euro of solvent. Don't need to go through a company who can do it for you, of course, but it's very simple, and you can directly test the separation ability of your column. Looking at the capillary system, it's much more complicated, because to fill beds in a column with a diameter of 50 microns is not easy. You have problem with frits. You know, the frits are very important to avoid that the stationary phase goes out of the column during the separation process. Also, we could just use this system, so a polymer layer adsorbed on the surface of the inner wall of the capillary, but in this case, you have very low beta values. The beta value is the ratio between the stationary phase volume over the mobile phase volume. So low beta value means low efficiency and low separation capacity. So looking a little bit more in detail in this size effect, so I have already mentioned that in terms of dimensions of the column, you go from millimeter to microns, 10 of microns for the diameter. If you look at the volume now, considering microliters, typical flow rates in chromatography are about 1 milliliter per minute, while for capillary system, you will go down to tenth or 1 units of microliter per minute. This is the same for the injected volume. Typical loop that we can use in chromatography are about 20 microliter, while in capillary system, you will inject only nanoliter. So it can be a problem, but it can be also an advantage if you have only teeny amount of sample, for example, for bioanalysis. So if you consider column of the same length, the volume of the column is proportional to the square of the radius. So you have 4 orders of magnitude less volume of stationary phase in a capillary system as compared to a typical system. So the idea is to prepare in situ the solid support, I mean the stationary phase, or the support for the catalyst, to prepare it directly inside the column through photochemical reaction. And which material we were thinking about? It's porous, permeable, and surface tunable materials. So typically porous polymer monoliths. So all of you know what is a monolith. It can be defined like a single particle, large particle that does not have interparticular voids. If you have particulate system, you will have always some empty voids between the particles. In this case, everything is linked together and you do not have such a voids. So you have interconnected pores. Interconnected pores is very important because if you see this transversal section of a monolith, so you have flow-through pores, which are quite huge in terms of diameter, which will allow a fluid to go through the monolith. It can be a liquid phase, it can be a gas phase. Then you have high mass transfer, high permeability. In the best case, you also have mesopores, so low pore size, to increase the contact area, the surface area. Of course, in France, we have, in Brittany, a very nice example of this monolith. Here it's just a picture showing that. So I hope, I just want to go to the next. Yeah. So this is how it looked like. So this was representing a silica-based monolith, but you have these porous channels, so the fluids can go through, and this allows to have very high mass transfer. So very high efficiency in the process. And in the best case, you have a mesoporosity, as I mentioned just before, to increase the surface area. So you have a high contact area. Okay. Other advantages of monolithic system compared to particulate system, that if you look at the H value is a quantitative data of the efficiency of the process, is the plate 8. In both cases, you will go for a minimum of H value. This means an optimal linear speed of the fluid going through the column. But if you want a process intensification, so if you want to increase the speed of the mobile phase, you see that for the particulate system, you will have an increase in H, so you lose efficiency. So this means you cannot make high throughput analysis because you will have poor efficiency in your result, in your analytical result. While for monolithic system, in theory, you do not have this increase in H value. So you can make the analysis faster and faster and faster with the same quality of separation of analysis. Also, and this is important in microfluidic, the monolithic phase provides less back pressure. This is very important because once you start with microfluidic, you are thinking you are more a plumber than a scientist. It's complicated. And a last comparison I would like to mention here is the comparison between liquid chromatography, capillary liquid chromatography, and capillary electrochromatography. In capillary liquid chromatography, you use a pump to allow for the motion of the fluid through the column. And you will have this kind of profile, a parabolic profile, where the speed is maximum at the center of the column and nearly equal to 0 at the wall. So this means that intrinsically, the use of a pump will induce a broadening of the peak, so a loss of efficiency. While in the case of electrophoretic system, you have a flat profile of elution. So you have a narrowing of the peak, which provides you high efficiency. And we will see later maybe one example. Okay, now catalysis. I cannot say much because I have experts in front of me, and we have already mentioned that this lowers the energy of activation, and it's regenerated after the reaction. Why I've selected this reaction? Because this is one of the first reactions I remember I did when I was a PhD, not a PhD, a master student in chemistry. This is the Clemensen reaction. So in the presence of zinc and in acidic environment, you will reduce a carbonyl group in methylene group. So from a ketone, you obtain an alkane. But what I remember also from my organic lab course is that sometimes you need, not sometimes, you need to recover the product. And sometimes you need to go through very time-consuming and tedious work. Filtration, separation, recovery, and so on. So taking the EU PAC definition about catalysis, you know that catalysis can be classified as homogeneous catalysis, in which only one phase is involved, or heterogeneous catalysis. In this case, the reaction occurs at or near an interface between phases. Now, with the area of nanoparticles as catalysts, we even talk about pseudo-homogeneous catalysis. Yeah? So this is a very nice example of use of heterogeneous catalyst, which is a magnetic catalyst. So you perform your reaction, you just put a magnet, and you can recover easily the product. And this is very advantageous because in this case, you can chemically modify the surface of the magnetic nanoparticles to, immobilize active site, catalytic site, and then the reaction really occurs on the surface of the catalyst, which provide very high efficiency and high yield. Okay, so I've learned a lot listening to you, and every day I was changing my presentation, and I removed so much that I don't say that I will finish soon, but I remove all the part about materials, about polymers. I thought, okay, this is not the question. I have to think. And then I was thinking, how do we do a reaction? Okay, we have seen very, very nice reaction using enzymes, but how do I perform it? Do I use a vial? Do I use a micro reactor, what I will tell you after? And can I monitor the reaction? Do I have to wait all this workup and to say, oh, the reaction did not work? Or can I, after 3 minutes, say, no, the conditions are not optimized? So in my sense, I will now try to combine these two ideas, miniaturization and flow chemistry. So going to micro-reactor technology. So micro-reactor technology is considered like the round-bottom flask of the chemist in the 21st century. For sure, there is still we need some proof of it. But it is said that it allows for easy scale-up of the synthesis. So you can do it in a 100 micron diameter flow reactor. It will be easy to do it in a 500 micron wide microreactor. You improve the profile of the product, so less side product, higher yield, and safety and easy process intensification. And this is mainly due because of the small reaction volume. If you use small reaction volume, some process parameters like pressure, temperature, residence time, flow rate will be easy to control. Also, if you have other potential of strongly exothermic reaction or explosive reaction, it's much more easy to control. It will make pff, instead of a big bang. And also, you have higher safety when you use toxic or extremely, extreme condition like high operating pressure. Now, I would like we take a few seconds on this slide. This has been developed by Sigma Aldrich, and it shows a very simple reaction, the neutralization of chlorhydric acid with sodium hydroxide. So when you mix both of them, you obtain a salt, which is sodium chloride, water, and heat. The reaction is highly exothermic. So if you compare two systems, this reaction made in batch, so this is for the case of a 5 cubic meter reactor, still at 500 RPM, and in a flow process. So here I just, it's not clearly seen, sorry, but the color corresponds to different temperature. So the blue is a temperature of 293 Kelvin, while the red part is a temperature of 303 Kelvin. So you see that when you do the reaction in batch, you have a gradient of temperature. And of course, it's cooler, the temperature is lower on the external part of the vask because it's cooled down with contact with air. If you do the same reaction in a flow process, so this is a transverse section of a microfluidic, so the length here are given in millimeters, so this is a distance of 1 millimeter. At the top, you inject chlorhydric acid and then sodium hydroxide. You see that in this case, you have much more homogeneous distribution of the temperature. You have a small gradient, but it's not so high. And after only a few millimeters, you have an homogeneous situation. So the problem with this gradient temperature, it creates hotspot in the reaction major. This means you have more risk to get side products. If in the case of a reaction A should be given B, you nearly just stop at B in the microreactor, while the presence of gradient of temperature can provide the formation of side reaction or even fragmentation. So there are more risks to get side products. Here is the same idea for the mixing. So still this model reaction, and this is a concentration, a profile concentration. So in blue, it's equivalent concentration of 0.8 and 1.2 in red. So even when you mix these two substances at high speed in a batch, the mixture is not homogeneous, it's not perfect. While in the case of a microreactor, here you have inlet A, so you introduce the chlorogenic acid. Then at the distance 0 where the reaction can start, you inject sodium hydroxide, and you see that nearly all along the microsystem you have an homogeneous distribution of the concentration. Only here you have an unstable regime. And all these positive effects of microfluidics are due to this very favorable surface to volume ratio. So for example, if you take a 1 cubic meter reactor, you have a surface to volume ratio of 0.06, while you go to 200 for microchannel with a size of 100 microns. So you come to surface dominated systems. Then I was thinking, okay, typically we do reaction in batch. So are homogeneous system condition extreme condition? Is it something exceptional to get homogeneous system? And also, manipulating tiny amount of sample, is it in extreme condition? Maybe we should add some inputs at this definition. Okay, before to go to some results that we had in my group and to conclude, I would just like to say another word, a little bit general word. You are all fascinated by solving the question, the problem of origin of life. And we understand that it's very much a problem of chemistry. But you all know also this huge chemical company, BASF, and the slogan, chemistry for a better life. So we should think also about chemistry like a way to improve our living. And going to this microfluidic and flow technology, you will see that you can meet much of the requirement of the 12 principle of green chemistry. You know that the principle of green chemistry can be summarized as the word productively. So in blue, I consider that you can meet this requirement using this combination of flow chemistry and microreactors. So you prevent the waste, you use a safe synthetic methods, you can use catalytic reagent, temperature and pressure are not anymore problems. You can have in-process monitoring. I will show you an example at the end of my presentation. You have less side products. This is the E-factor ratio about waste and products. Low toxicity of chemical products, you use less, and it's safe. And of course, you can have a microsystem in parallel. So there are literature data which give you the amount of product which can be produced per hour or per day. And this is the same for the 12th principle of green engineering. And you know that this 12th principle of green engineering, catalysis is at the heart of this principle. So we are dealing with some, I think, very important today issue. Okay, I will not give many examples of what we did in the lab. As Kosuke said, we are mainly polymer scientists, so we've been working a lot on polymer metal nanoparticle composites, and in PPS we reported a review. I will just give you after an example about the use of monolithic materials in a microchip for separation, pre-concentration, and detection of peptides. I will show you also how photochemistry approach can allow you to specifically locally control the surface functionality of a monolith, and then you can have different sections along the same column. For example, if you want to do cascade reaction, you have a section 1, section 2, section 3, and different catalytic reaction can occur. You can change the length of the different sections, so you can do a lot of things. And we've been working on chiral system for enantiomer separation. Okay. So I will give you example of analytical chemistry, heterogeneous catalysis, and the main topic of the materials will be monolith and hybrid monoliths. So our general strategy is to immobilize a monolith inside the column and then to deposit. Here the case is a bit restrictive, but not only metal nanoparticle, we use mainly metal nanoparticle as catalyst, but let's say active species. And it could be catalyst, it could be a ligand, it could be a selector, it could be nearly whatever you want. It could be an enzyme. So I will not go deep in the chemistry, but a monolith is not difficult to prepare. You just need to have the good recipe. It's like cooking. So what we were interested is using this monomer N-acryloxysuccinimide because it has this reactive group. So we can, when you make a mixture with a crosslinker, with a porous gen system, you can obtain a very well-defined porous structure. And in this case, this is highly cross-linked system. So there is no swelling problem. So the material, you can go from water to hexane, come back to water. The material is not it's not damaged, so it supports extreme solvent conditions. The surface area is quite low. Porous volume is very high, and the diameter of the sphere is about 1 to 2 micron. I say sphere, I should not, because don't forget, all those spheres are stick together. There is no void between the stick. It's only one molecule. So we can develop this material on different substrate and within different substrates. For example, a glass slide, you can get these porous films. And this can be used like thin layer chromatography, or we use it also as a surface enhanced Raman spectroscopy sensors. You just deposit your sample, you have gold nanoparticles, and you detect directly with a Raman microscope. Within microchannel, of course, to prepare lab on a chip or microsystems, microtasks. And also, we also were able to synthesize them within micropipette tips. So just if you have here a specific ligand, you can just use them as solid phase extraction. You can prepare a sample, pre-concentrate. For example, you make flowing 1 milliliter, you concentrate your species, you elute with 100 microliter, and then you have concentrated by a factor 10. Okay, so you just, I don't know why, but you just feel the inside of the capillary system can be a microchip or just a capillary, like in this case, with the reactive solution, you irradiate, and at the end you obtain the porous system. Yeah? So we have some functional groups, so we can graft selectors like molecular entities, or as I wrote here, hard and soft particles. For me, hard particle is a metal nanoparticle or metal oxide, and a soft particle could be an enzyme or a protein. The specificity of this system, and this is why I'm talking about it today, I like it very much, is that during the reaction, you also generate some hydrolysis of the group. So you generate carboxylate, carboxylic acid, carboxylate group, depending on the pH. And this works like an electroosmotic pump. So this means that the surface of the porous system is negatively charged. So you have the formation of a double layer of cation. And when you apply a voltage, you have a flow going to the cathode. So you don't need a pump, you just need 2 electrodes, and you can make fluid system fluids through the porous materials. Of course, you can change the size of the pores depending on the preparation conditions, and as I told you, they are not the name of the solvent, but this is the less viscous, this is hexane, and this is water. You can change the solvent. You have a linear dependence on the back pressure of overflow. Okay, you need to fill up, these are the experimental data. You need to be sure that the polymer is anchored on the wall of the capillary and so on, but let's go over. I will not show you any example of separation, just as summarized here. So what we could develop is chromatographic column with hydrophobic segments. So typically it's the C18 columns. And we could separate proteins, peptides, amino acids. We could also prepare hydrophilic columns for this. I don't know if you know it, but probably is Illic mode, hydrophilic interaction liquid chromatography, which is very, very good to analyze, for example, adenine, guanine, and cytosine over polar molecules. So we could separate them, and also some chiral molecule. So the liquid phase separation method can be very complementary to gas chromatography. Gas chromatography does not allow you to separate protein or peptides because you will degrade during the thermal process. So it's quite powerful method. And as I told you, because of this surface charge, you can use it over some pH. I still have 10 minutes, right? Okay. So I would like to give you another example of analytical chemistry. This is the way we use these materials to pre-concentrate peptides. So what we used is, it's not the same monolith in this case, it was a monolith with phosphate group. So you know what are the typical steps for microchip analysis with pre-concentration step. So first, you load the samples. You have here, so this is a cross microchip with 2 channels. One channel will be used for injecting the solutes, and also and another channel for the separation. So here you have a small section, like 1 millimeter of a monolith materials. So you make flowing the peptide solution, you pre-concentrate, then you elute, and online you make a separation. So to synthesize this very small section of monolith, we use the UV lamp of a microscope, of a fluorescence microscope, which emits at 365 nanometer for the excitation. So we could just use the microscope to polymerize inside the channel the material, and we could so obtain, depending on the composition, you see a small section of about 350 microns of polymer materials inside the microchannel. Then we used so the monolith inside the microchip for pre-concentration. We use a mixture of peptides, and it is expected that only phosphopeptide will be collected on the monolith. So you make elute all the other species, and then you can separate them. So we have a pre-concentration step, and you can see here, this is the fluorescence images. Unfortunately, they are in black and white. So if you increase the intensity if the fluorescence intensity increase, means that we concentrate more and more phosphopeptide because we used a fluorescent phosphopeptide. So then we can concentrate. And at the end, we just make the elution step. I will go over this one. So we concentrate the phosphopeptide, and then we can elute directly within the microchannel and separate them. So we have online pre-concentration and separation and detection. I would like to say a few words about hybrid monoliths, and they're used for catalysis, of course, and for online monitoring of a reaction. So here again, we use photochemistry. The idea is to immobilize amine groups on the surface of the porous materials, because amines can really chelate gold nanoparticle in a strong way. It was mentioned in one of the presentations yesterday, I think, or before yesterday. We also use hyperbranch polyethylene amine, and this was also working very well. So what we see that we have polymer nodules which are decorated with gold nanoparticles. And we made a lot of experimental run, and we bought commercial nanoparticle. We also synthesized in situ the nanoparticles, and we obtained different type of morphology. And these two types of morphology really were quite interesting for us, because here you see really finely dispersed 20 nanometer size gold nanoparticle. There is no aggregation, and we were thinking that probably this could be a good candidate for heterogeneous catalysis. In this case, you see some kind of aggregation, and then we were thinking about applying this substrate as surface-enhanced Raman spectroscopy substrates. Because if you have aggregation, you will have hotspots and you will have enhancements of the signal. So this is what we did here. And if you look a little bit with a closer look, it's not spherical nanoparticle. We made a special method to get flower-like nanoparticles. They are dendritic-like. And this made me think about, this is where we took the picture, the group photo yesterday. It's a bit in the same way, flourishing nanoparticles yeah, outside. And as you know, Raman spectroscopy is expected to be used in the future as a very sensitive method, because in theory you can detect one molecule. It's a very powerful method. So I think it's maybe not very well seen here, but here you see the capillary. You see it's about 200 of microns, and we directly place the capillary below the microscope, the Raman microscope. We made flowing a solution, and then we could directly detect. Here we have a limited system. We go to 10 to the nanomolar system, but you can go to pico and femtomolar detection level. So about catalysis, I will take a very, very simple example. It's the rejection of nitro compounds. So in the presence of a rejectant, sodium borhydride and gold nanoparticles, you just reduce the nitro group in amine group. The reaction is really known. There is no invention in this, but it was for us quite easy to follow, because the nitro has UV absorption, absorption in the visible, while the reduced compound have absorption in the UV. So by simple UV spectroscopy, we can monitor the yield of the reaction. So what we used is a microreactor. The internal diameter was 75 microns. Length of the reactor was 3 centimeters. And we just inject the nitro compounds. The gold nanoparticles are inside the 3 centimeter microreactor, and we mix with sodium borhydride. And what we monitor is the UV, it's the visible absorption at 400 nanometer of the reactant. So what you see is that when we decrease the flow rate, the absorption peak of the nitro compound decreases, because when you increase the flow rate, when you decrease the flow rate, you increase the residence time. So you let enough time for the reaction to proceed. As I told you, using photomask technology and photo-driven grafting, we can, along the monolithic column, really locate precisely the gold nanoparticle. So for example, here, this is a native monolith system. So this is the porous material. As the pore size is about 1 micron, it is of the same order of magnitude that the wavelength of light. This is why it appears as white. But the black area, it's where we have deposited specifically gold nanoparticles. So the idea was, okay, let's take a little bit longer system. So in the first 3 centimeter of the microsystem, you have gold nanoparticles, so a catalytic active substrate, and then we have a kind of separation column. So if you inject the nitrobenzene with the sodium only, without sodium borohydride, you get, and of course I didn't mention it, but at the end of the column we have an online detection. So you obtain a peak which corresponds to the nitrobenzene. Then if you add the second reactant, this means sodium borohydride, you have still the reactant and formation of the product aniline. Then you can directly online monitor the yield of the reaction, and you can adjust the concentration of both reactants. Of course, if you increase the concentration of sodium borohydride, you consume more and more the reactant, and more product is obtained. So you can follow, monitor online in real time the process of the reaction. Okay, I think I will come to conclusion. I just want to say that we can also synthesize the nanoparticle by a photochemical method. This is very interesting because we can have a mixture. So monometallic system, bimetallic system. So we can mix 2 metals, there is no aggregation. And what we can do is to have, along the same microreactor, different metal. So we can have cascade reaction, for example. And these systems are very, very efficient. So in conclusion, the main topic of the symposium is extended view of catalysis. And yesterday during the group discussion, I think we were all wondering what is a catalyst. Now I'm thinking, should we have an extended view of extreme condition? What is extreme condition? And Kosike with his poll showed us that, okay, we full agree on some basis, but maybe we have different view. In my case, homogeneous condition is in a way extreme condition because it's not happening very often. Also manipulating tiny amount is an extreme condition. And what I think is that combining different views, we can create high potential, for example, material science with porous materials I showed you now. And I don't know what it does not appear, but there was also, I did not talk about it today, but what we are thinking about is to, for very specific reactant, which can be toxic, is to generate in situ the reactant. For example, you generate hydrogen directly inside the column. And then nanoscience and nanotechnology for the hard and soft nanoparticles, surface chemistry, which is related to these 2 areas, and microfluidics, organic synthesis, because we are all interested in catalysis aspects, and I've learned a lot of things about biocatalysis and specific recognition. So I would like to thank you for your attention and to thank for the extremely good organization. Thank you. And I would like to thank some of my coworkers.
Thank you so much, Ben, for the inspirational talk. Let's take some questions from the audience. Anyone? I actually see a lot, like a future implication, like one of the potential future implication of this is to, for example, see if you can graft, for example, rare earth element inside these capillaries. And that way you can actually directly measure or monitor the reactions that could be taking place, such as like those local conditions you can find from like in a geochemical context. Do you actually see this type of application will be possible?
Yes, I think to immobilize this rare earth element, you need the good chelator. So I think you need to think about the molecular chemistry and then to immobilize. But with this photochemical approach, thiolene chemistry, it's very powerful because from a, I would say, a generic surface, you can photograph different molecular species. So if they are commercially available, it's much more easy, just buy and graft. If not, you need a little bit organic synthesis workup, and then you can figure out.
And from that sense, you can also do the photochemistry too, in situ.
Yes, yes, yes. And for example, we can also do photocatalysis. Yesterday, there was a talk about photodegradation of eosine. So you can have photocatalysis because we use the UV transparent microsystem.
Thank you. Yes.
Thank you for your talk. You described microreactors essentially being the new beaker for chemists. How generic are the different systems, or would you need, depending on the reaction, either a longer or shorter system, in which cases are you really setting up very custom systems per reaction, or are most reactions pretty generic?
Yeah, it's a good question. In fact, it depends on the complexity of the reaction because you need as many input as reactant you need. So you need to design a proper microreactor for a proper reaction.
Thank you so much.
We still have time. Any other questions? I think Ben is also looking for a collaboration.
Yeah.
So maybe many of the people in this audience are more interested in the origin of life, but if there's any venue, not only about the productivity, but also life, then
Yes.
I think it'll be a really interesting collaboration. Let's see. Tristan.
Hey, thank you very much for your talk. So you were talking about it being like microfluidics being a really nice platform for looking at different kinds of extreme environments. And I know that from other labs, sometimes people are even using them at high pressure conditions, but there's of course limitations.
Yes.
From your perspective, what would be like the major limitation in engineering for kind of extreme environments using microfluidics?
The first limitation is about the reaction by itself, because if you have a compound which precipitates, for example, the flow is stopped. Also, some groups are working on polymerization. But if you get a polymer, you will change the viscosity of the fluid. So it becomes also a kind of complexity. So for the extreme condition, it depends on the resistance of the microsystem by itself, I would say, for pressure, for temperature, and so on. But from point of view of chemical reaction, I think there is a lot of limitation for all this kind of providing high molecular weight compounds or a little bit non-soluble products. And if you need to because a lot of products you can just recover them because they just precipitate and you filtrate. In this case, it's very difficult. So you need that the system remain homogeneous along the process.
That's actually, so immediately that brings to mind the fact that, like, for example, I use gold tube reactors for hydrothermal experiments, and that's a limiting like experimental container because you have to think about which reactions might actually be activated by gold. And so that'd be a really good thing to consider for these types of reactions is what's the best container, the best system.
Thank you.
Okay, so I think the time is up. So let's thank Professor Carbonnier once again.